Waukesha Foundry has been producing intricately shaped cast metal components since they were established in 1912. Their manufacturing capabilities have allowed them to meet individual customer casting specifications and quality requirements for nearly a century. Waukesha Foundry specializes in casting components for aerospace applications, marine components, pumping equipment, and military applications. For our team's project, we were tasked with looking specifically at the casting process for military tank wheels.
Sand casting starts with design on paper and ends with a finished metal good. Let's say, for example, that you would like to produce this metal piece. First, you are going to need to make a pattern out of wood. This pattern can then later be pressed into a sand mold to create its negative image, also known as the mold cavity. The sand mold itself is made up of a top half called a cope and a bottom half called a drag. A central piece called a core may be required if the final piece is supposed to be hollow. Once the top and bottom molds are glued together, molten metal alloy can be poured through a series of gates and filters. Once the metal cools and the sand broken away, the resulting cast metal piece can then be machined into its finished good state. Let's take a look at this in action. Here, you can see carefully created sand cores that represent the hollow center of the final tank wheel. They are coated with a spring-on heat sealant that prevents sand from flaking off during the pouring process. The wooden housing shown here is the mold frame that will soon be filled with a mixture of sand, adhesive binding agent, and catalyst. The skilled line worker shown here is carefully filling the mold housing with this pre-mixed 3-part mold material. The sand is filling in all of the space around the wooden pattern we discussed earlier. Notice how the sand is currently loose. Once the frame is filled and the excess sand removed, the mold frame continues down the line to the mold press. This is where the sand is packed down using a combination of pressure and vibration. Here's a picture of the mold press that is currently in place. The mold is then baked in an oven before the wooden frame and patterns are removed. Line workers then use overhead cranes to glue together the top and bottom halves. Now, the sand mold is ready for the casting process.
Now we have reached the heart of the casting process, the melting on the pouring steps. Raw metal can come from 3 sources. It can come from new metal, reused metal from a previous batch, or scrap metal purchased on the open market. Here you can see this metal being placed in the furnace, which reaches temperature up to 3,000 degrees Fahrenheit. Here the melting scraps oxidize metal off the top of the mixture. If this defect were to be left in the mixture, it would cause downstream defects known as inclusions.
Oxidized metal is consistently forming the longer that the molten alloy is exposed to the air. Our observation of this process identified multiple human factors that can introduce variability into this process step. Here, you can see the temperature of the molten alloy being taken. After the metal has reached an appropriate temperature, the melter motions for the forklift driver to move the preheated ladle into place. Preheating of the ladle is necessary so that the temperature differential does not damage the manufacturing equipment. Here, you can see approximately $30,000 worth of raw material being poured into the ladle in the form of molten alloy. This alloy has undergone stringent chemical analysis to make sure it is of the correct consistency and concentration before they reach this point.
Now that the molten alloy has been poured into the ladle itself is moved into place using an overhead crane system. As you can see here, all of the sand molds for this batch are lined up in order to minimize time between pours. Before the first pour can take place, the temperature of the molten alloy needs to be within a specified temperature. In this case, the temperature is too high, so the pouring foreman instructs his team to hold off until the ladle cools. It is important to realize that this idle time is non-value added and allows additional unwanted oxidation to occur. This initial overheating of the alloy mixture was observed during each of the 3 batch processes we were shown. Keep this in mind because it plays into our recommendations later on.
It is at this point in the process where human factors really begin to play an integral role in the final quality of the cast metal part. It is up to the experience of the foundry pourers to quickly and consistently fill the molds with molten alloy, and then move on to the next mold. Factors such as the vertical distance of the pour determine how smoothly the metal flows throughout the gating system of the mold. Temperature of the alloy is taken between pours to ensure that the alloy remains within the specified temperature window. Waukesha Foundry currently employs 3 experienced pourers and is in the process of training a 4th. All pouring currently takes place during 3rd shift.
Now that pouring is complete, the mold will be left to cure overnight. After the appropriate cure time has been reached, the sand mold is broken away, exposing the cast parts. The sand from the mold is then placed through a recycling process so it can be used again. This cast part now includes cast metal from the pouring process. Here you can see that the tank wheel also includes cast metal in the shape of the pouring gating system. This part will be cut away from the final machining takes place.
Inclusions are process defects resulting from multiple sources of variation. Here, you can see cast metal parts with clear, pitted surface defects. These surface inclusions are caused by either oxidation of metal during the pouring process or from sand flaking away from the mold cavity. Once these surface defects are identified, they are ground down and then filled with welding material. All of this is considered rework, and our semester project was primarily focused on reducing inclusion occurrence rates.
Once all of the inclusions have been welded, ground, and machined, the parts will undergo random sampling to meet predetermined quality standards. These quality checks include a visual inspection of the part surface, as well as imaging of internal structure using ionizing radiation. Now the finished parts are created and ready for shipment.